My name is Macy Gottschall, and this is my final oral presentation for Experiment 1, which was What's in the Water. The purpose of this experiment was to identify unknown compounds present in a drinking water sample. So to do this, we used IR and NMR spectroscopic software. So first we had to understand what IR and NMR were. IR is infrared, and it shows the presence of functional groups in the sample in which you are testing based off of where the peaks are in the graph that the experiment would produce. NMR is the nuclear magnetic resonance, and it shows specifically the number of hydrogens in the sample that you're testing and roughly the amount of each based off of the area under the peaks in the graph it produced. This table here is about functional groups. Here are the possible functional groups, and this is the ranges in which they occur on the IR graph. So when looking at the IR graph, if you look at where it spikes up, or in this case, spikes down, so reverse the graph, these are the ranges in which these specific functional groups would be present. This figure is Lewis structures. These were used to fill out the pre-lab charts of NMR and IR. So for the IR, we looked specifically at the types of bonds in each. Based off of what was present, we were able to check off what functional groups were present in each of these possible compounds, which had the potential to be present in our sample. And then when we're talking about NMR, we're obviously once again referring only to the hydrogens. So we looked at the hydrogens present in each of these Lewis structures, the different types and the amount of each, because the different types gave us the number of peaks and the amount of each gave us the ratio. These are the IR and NMR pre-lab charts. So right here are all the molecules that had the potential to be present in our sample of water. Using the Lewis structures on the previous slide, which was given to us in our lab manual, we checked off which of the functional groups was present for each of the compounds. Here is the NMR evaluation. Once again, these are the molecules that had the potential to be present in our sample. Looking at those Lewis structures, we were able to determine the number of types of hydrogen, as you can see here, and the ratio of each, which also correlates to the area under the peaks in the graph that would be produced by an NMR test. For the experimental procedure, because we ran an NMR and an IR test. For the IR, we were each given a specific vial. So for example, mine was vial 20. Once we assembled the pipette, which was, the glass part of the pipette, any pipette ball, we made sure that we had a brass ferrule placed in the center of the IR machine, which is right here. Once the brass ferrule was centered on top of the diamond crystal in the center there, we put our liquid 1/2 to 2/3 of the way full into that brass ferrule. From there, the spectra was run and our data was printed after the computer developed the graph. For cleaning, the brass ferrule was placed in a dirty brass ferrule beaker, and all glassware was disposed of properly. To clean the platform, we used a cotton ball and alcohol. For the NMR, once again, we had a specific vial. Once we took that vial out of the test tube holder, it was put into a spinner because that is how NMR tests are run. To put it in the spinner, we used a height adjustment block. After that, we put it in the sample compartment, which is located at the top of the NMR machine. From there, the spectra was run and our data was printed. The IR results of vial 20. After running the spectra, you can obviously see that there are multiple peaks present on the IR graph. These two right here represent a C bonded to H benzene ring and a C bonded to H singly bonded carbon. The most prominent peak, way down here, is in the CCl range, but we can consider it irrelevant actually because of the fact that benzene rings can produce peaks down in that area. These are the NMR results for vial 20. Obviously, you can see there are 2 peaks present on the graph. That means there are 2 peaks that we should put in here, and there are 2 types of hydrogen. The area under this first one here is 1, and the area under the second one is 1.5. So when we were trying to calculate the ratio of areas, we doubled them, so we could be dealing with whole numbers. Vial 20 identification. After comparing our experimentally printed data to the pre-lab data, we were able to determine that vial 20 included paraxylene in the sample. We did this because, according to the NMR, there were 2 peaks in a ratio of 2 to 3, and no other possible compound had those specifications. And then for the IR, there was a C bonded to H singly and a C bonded to H benzene ring. And once again, paraxylene was the only one to match our experimental data. Paraxylene, when ingested, can cause hazards. For human health risks, it has effect on your memory, your motor functions, your balance, anything of that nature. It can also cause organ irritation in the form of your skin, your stomach, your kidney, your liver, and in severe cases, it can also cause unconsciousness and death. In the environment, it also poses a risk when ingested by animals or humans, because we are an animal. It has negative effects on 6 of the 11 bodily functions. So, for example, it negatively impacts your gastrointestinal, your central nervous system, your renal, your reproductive, and quite a few more. Actually, just a couple more. But still not something you want to be ingesting, because obviously it's not good for you. So all in all, the goal of this experiment was to figure out what was in our sample, and we used NMR and IR testing to do this. For my vial 20 identification, we printed IR and NMR graphs. For IR, there was a C singly bonded to H and a C benzene ring bonded to H. Excuse me. Obviously that led us to paraxylene. And then for the NMR, with the ratio of 2 to 3 and the presence of 2 peaks, once again, paraxylene was the only viable answer. And then, obviously, when ingested, it causes hazards. Those are my references. Thank you.